Hi, my name is Matthew Finlay, and this is my Lab 4 on bar magnets. All right, begin. Our purpose was to measure how magnetic field strength changes with distance using bar magnets, and then compare the experimental results to computational predictions. Our materials were a bar magnet, meter sticks, tape, a magnometer phone app, and then GlowScript. And our system was the bar magnet and Earth, and the surroundings was everything else in the environment. Important principles included Biot-Savart law, which describes how the magnetic field at a specific point is generated by a small segment of electric current. Next was magnetic field of a dipole, which defines the magnetic field created by circulating electric current. Since bar magnets behave like magnetic dipoles, this formula can be used to model their fields. And the last one was the distance dependence formula, which is the magnetic field strength of a bar magnet decreases as the distance of the magnet increases. All right, for the actual experiment of the lab, we first positioned the phone so that it was perpendicular to Earth's magnetic field. Then we located the position of the phone's internal magnometer and marked it with tape. For the next part of the lab, we measured the distance between the magnometer and the bar magnet along the magnet's axis for each of the following magnetic fields seen below. Now here's the actual data from the experiment. For each trial, we ran 3 different experiments and averaged them out over the course. And as you can see to the right here, here's what our graph looked like. Our slope was negative 1.6644, and then the y-intercept is negative 16.759. And this is used on the next slide to actually do our calculations. All right, now here's the actual calculation for the dipole moment using the slope from the previous slide as well as the y-intercept. The value that we actually found was 0.26. The next part of the experiment was finding the actual perpendicular component of the magnetic field. This was done by first solving for dperp, which is 0.12, and then using Pythagorean theorem to find the actual d value. Eventually, we would find that our net magnetic field value was about 286 microteslas, as seen to the right here. And then here is the actual experiment being done at the top of the screen to the right. And here's our actual computational model. Here, just plugging in the values for dperp, as well as mu-mag, just ones that we got on the previous side, and we have a function that calculates the dipole moment v. We just calculate r mag, r hat, found the actual b value using the equation that we used from the previous slide. And then here's just the inputs for the actual values in code. And then to the right here is the actual results for our computational model. You can see the arrows for the perpendicular axis as well as the parallel axis. And then our d value is 0.169706. And then the b, which is that arrow, the b the b at a 45-degree angle was located at like 2.65, 7.97, and it had a magnitude of 8.41 times 10 to negative 6. So our final results were off slightly, and this could have been done due to a multitude of reasons. For example, our assumptions were that the bar magnet was modeled as a simple magnetic dipole. Earth's magnetic field was ignored in our computational analysis, and then additionally, some sources of error could have been nearby electronic devices or metal objects. The position of the phone's magnetometer might not have been marked correctly, and then just minor human errors when it came to actually measuring the distance could have caused errors. Getting into discussion question 1. So, if the experiment hadn't been aligned with magnetic north, then the total magnetic field would have been the combination of Earth's magnetic field and the field produced by the bar magnet. And so this overlap would have distorted the readings, leading to incorrect distance calculations and overall skewed results. And then lastly, for the last discussion question, if 2 identical magnets were placed end to end and the experiment was repeated, the direction of the magnetic field would have remained the same, with the strength of the field would double because the combined dipole moment would be twice as large.